So, I have been discussing about these two papers of Cahill and Glauber. So, last class we discussed about this example which is quite useful example I must say. So, which is like you so now we are talking about the I mean expressing any operator which is bounded operator. So, bounded operator in the sense that if I take its norm which is square root of trace of f dagger f. So, this is finite. So, then it is bounded operator, and we have seen that any such bounded operator can have the representation in terms of displacement operator together with this weight function. So, d alpha is my displacement operator and then d of minus alpha. For bounded operator this and we know that if f is bounded, then this is square integrable function. So, now let us take this example which we discussed last class also. So, f lambda is equal to lambda to the power a dagger a, where lambda is a complex number, right. So, we have seen that f lambda this is bounded. So, for lambda less than 1. Similarly, f lambda is trace class. So, trace class means that f 2 which is trace of square root of f dagger f, this is finite. So, this is trace class. Okay. So, f is trace class. Again for the same region, and f lambda is finite. So, finite means that its f 1 norm which is square root of least upper bound over psi such that psi is equal to 1 of psi f dagger f psi. So, this is finite. So, then we say that f is finite operator. So, this is finite for lambda less than equal to 1, right. This is what we have discussed last time. Okay. Good. Now, we so what we have seen earlier that so if f any operator f, if I can have, so it does not mean that I always have such in a normal ordering. So, this is normal ordering. For bounded operators, most of the bounded operators will have that normal ordering in the sense that this is convergent, this series. Okay. This is a convergent series, right. And we have seen that when you use this representation in terms of displacement operator, then this coefficient C n m, it has this form 1 upon n factorial m factorial 1 upon pi alpha belonging to C d square alpha trace of f d alpha, this is the weight function, multiplied by e to the power minus mod alpha square by 2 into minus alpha to the power n alpha star to the power m, right. This is what we discussed. Similarly, we will have expression for coefficient in antinormal ordering, symmetric ordering, etc. And now we have, so generically what from here you can show is that these coefficients are I mean generally bounded. So, in the sense that this is n plus m factorial square root of this divided by n factorial m factorial into this is the Hilbert-Smith norm. Okay. So, if this is finite, then of course, this will be finite, this is bounded, but of course, finiteness of this does not necessarily mean that this series is convergent. This series will be generically, I mean for most of the bounded operators one can show that this series is convergent. Okay. Now, for this example, this is what we wanted to figure out, that for this example, this one, what will be the so what will be the CNM? So, CNM lambda basically for this f lambda, right. Okay. And we said that you know, if you take this expression for f lambda, then it satisfies the differential equation d f lambda d lambda, which is basically of the normal ordering form a dagger f lambda a, right. Okay. I mean this you can verify from here, and of course, if I take lambda is equal to 1, then it will be identity operator, right. For lambda is equal to 1, this is identity operator, right. Okay. Now, I think we mentioned that what will be the form of this f lambda. Did I mention that? What is the form of f lambda? CNM, yes, not f lambda, CNM, yes. So, yes, so for CNM, what is the expression for CNM? Let me see. Yeah, that is the thing. Yes, let me see. I think we calculated it. Okay. Yes. So, yes. So, basically, this one is, I think this is the forms delta nm divided by n factorial into lambda minus 1 whole to the power n. Okay. But I do not think we have derived it. There was some issue how to derive it. Well, what I think we discussed that you can start with this form like f lambda is equal to sum over n m is equal to 0 to infinity C n m lambda a dagger to the power n a to the power m. Okay. You take this and then insert in these differential equation, and also you will have to use this condition, initial boundary, whatever you want to call. Then you know it is not difficult, you can show that this is the case. Okay. So, basically what you should do is maybe I will just mention just a minute, I will just So, if you use this thing, this expression here, okay. So, what you will get is the following, that d of C n plus 1 m plus 1 lambda d lambda is equal to C n m lambda. Of course, n and m star runs from 0 to infinity. Together with that, because of this, what you will get is d of C 0 0 lambda d lambda is equal to d of C 0 1 lambda d lambda is equal to d of C 1 0 lambda d lambda is equal to 0. Okay. How do you get that? I mean, just you put on the right hand side this expression, on the left hand side you will have to take derivative of this thing. Okay. And what does it mean? This means that for lambda is equal to 1, okay, for lambda is equal to 1, if I look at this series for lambda is, so this is for f lambda, if I look at this series, then C 0 0 is 1, it will always be 1. Always be 1 means what? I mean,
for all lambda.
No, this is for lambda is equal to 1.
So because d by d lambda C 0 so lambda is also 0.
No, we will come to this later. First, if I look at these and take lambda is equal to 1, then you see that C 0 0 lambda is equal to 1 is 1, right? And what about the other coefficients? All of them, rest of them are all 0.
No, I mean, wait.
So, I am talking about f lambda at lambda is equal to 1.
Exactly, yes.
So, the coefficient corresponding to n is equal to m is equal to 0 is C 0 0 lambda is equal to, I mean basically C 0 0 lambda, and at lambda is equal to 1 that has to be 1, right, okay, and rest of them all are 0. So, C n m, so therefore, what I am saying is C n m lambda is equal to 0, I mean lambda is equal to 1, this is 0 for n m not equal to 0 0, okay. Is that clear? Okay. Now, how do you get this thing? So, you know, this is because of you have a dagger on the left hand side, a on the right hand side. So, here on the right hand side, if you take this series, you will have a dagger to the power n plus 1, a to the power m plus 1. On the left hand side, you have simply this one, I mean d c n m d lambda, a dagger to the power n, a to the power m. So, to equate this, because you know all these operators, a dagger to the power n, a to the power m, for different values of n and m, these are all independent operators. Okay. So, from there you will see this thing, and this if you solve it, you will get this solution. It is not. So, this is basically diagonal, okay, right, and as a result f of lambda is in this form. This is n is equal to 0 to infinity lambda minus 1 to the power n by n factorial, a dagger to the power n, a to the power n, okay, isn't it? And this is symbolically written as, in the normally ordered form, exponential of lambda minus 1 a dagger a, okay. This is what we will see, okay, right, okay. And so, you can now figure out the other expansion in terms of the symmetric order and antinormal order. So, that is fine. Okay. So, now it is, so let me, I will not go through all the calculations, but I will just mention to you. So, let me erase this part. So, what about the symmetrically ordered coefficient? So, basically what I am considering now, f lambda is equal to, I mean this is not just for f lambda, any bounded f. So, n m is equal to 0 to infinity b n m lambda. Now, it is symmetric ordering. So, a dagger to the power n, a to the power m. Okay. This is the symmetric ordering. And once again you know that so basically this b n m lambda, this we discussed also last time. This is n factorial m factorial into 1 upon pi alpha belonging to c d square alpha, the weight function trace of f lambda d of alpha. Then here there will not be any exponential. So, this is just simply minus alpha to the power n alpha star to the power m. Okay. This is your coefficient, and yeah. So, if you use this form of f lambda and all that, what you will see is that this is equal to e to the exponential mod alpha square by 2 divided by 1 minus lambda into.
So you are talking about this lambda to the power a dagger a operator.
Lambda to the power a dagger a, only this one. Yes, yes. I mean this expression is true for any f.
Yeah, you can.
But
Now replacing that.
yes, yes. So, this is exponential of minus mod alpha square divided by 1 minus lambda. I mean this is, if you do this calculation with this form, this is what you will get. Okay. But of course, one should be careful, provided real part of 1 minus lambda is positive. Okay, because you had to do the Gaussian integral, and that Gaussian integral demands that this real part of 1 minus lambda has to be positive. Okay. I mean basically, yeah, you will have to do integral something like this, d square beta exponential of lambda minus 1, or let us say minus 1 minus lambda beta square plus alpha beta star minus alpha star beta. So, lambda is complex number. So, in order that this integral exists, what you should have is real part of this has to be positive. Okay. And this means that basically this means that real part of lambda has to be less than 1. Okay.
So if that is not the case, then it does not have a symmetric ordering expression.
If that is not the case, then this is not finite. Okay, this will have singularity, and therefore, the symmetric ordering expression may not converge. Okay. Now, of course, you know that this operator is bounded for bounded and also a trace class if magnitude of lambda less than 1. Okay. Now, magnitude of lambda less than 1 automatically tells you that, what does it tell you about real part of lambda? It has to be satisfied, right? But the converse is not true. Because real part of lambda may be less than 1, but still magnitude of lambda can be greater than or equal to 1, right? That may happen. Okay. So, boundedness of this operator or trace classness of this operator automatically guarantees that the symmetric order expression exists. Okay. Okay, good.
So earlier you said that the this f lambda is bounded and trace class if the absolute value of lambda is less than 1.
Yes, yes.
Which means the solution would be circle.
Yes, I mean not circle, disk, circular disk of radius 1. I mean within the within that. Yes. Now real part of lambda less than 1 means what?
So it's the full left side plane. So
Yes.
Even if it's unbounded,
Let us
you
see.
have a symmetric
This is
representation.
imaginary lambda, this is real lambda, and this is my unit circle, right. So, this is the region, I mean excluding the boundary, this is lambda less than 1, right. And what about real part of lambda less than 1?
It's the
Yeah. So, basically, yeah, this region.
No, but it can go.
Oh, sorry, yes,
the full plane.
yes, from this side, yes.
Even if it's unbounded, it can have a symmetric representation.
It can have, yes, it can have. I mean that is what I told in the beginning, that even for some unbounded operators you can have symmetric representation.
So also for the normal ordering case,
Hmm.
it will have normal ordering representation despite of whatever lambda is.
Exactly,
For
Exactly.
the entire plane.
exactly,
Okay.
exactly. Yeah. See, if this exists for symmetric ordering, of course it will exist for normal ordering. Okay. Yeah. So, this is why this example is quite interesting example, that even if it is unbounded, still you can have such expression, the symmetric ordering and normal ordering. Okay, good. So, okay,
Just a question. So,
yeah.
this is just a criteria that D and M should be the integral should have no singularities, right?
No singularities, yes.
When we put it back in the expression for f, and this series might not converge. Maybe the condition for series convergence would be stronger, that mod lambda should be less than 1. That should be within the disk. Whereas the condition for just B and M not having a singularity would be this.
Exactly. No, for series convergence, you will have more restriction here,
Yes, there will be more restriction.
more restriction. Yeah. So, this is just the finiteness of the coefficient.
Yeah.
So, for series convergence you will have more restriction.
So
Okay.
by series conversion, you mean that this B and M as a two valued this, you think of it as a sequence, and either n or m or both going to infinity, it should be convergent. That's what you mean by it.
Yeah. So, series convergence means that, yes, you are right. So, basically what you can think of is that if I take n is equal to 0 to capital N and m is equal to 0 to capital M, B n m lambda, then a dagger to the power n, a to the power m, this series. Okay.
Okay.
So,
This
this,
operator,
so let me call it as S n m lambda. Okay. Right. So, when we say that series converges, it means that limit n and m going to infinity, S n m, this exists and finite. Okay. So, even if these coefficients are all bounded, still there is no guarantee that this will converge. So, convergence of the series will put more restriction, of course. Okay. Good. So, So, let me write down the expression for the anti-normal ordering. So, f lambda d n m lambda a to the power m a dagger to the power n. So, these are the coefficients, and once again this we have discussed I think earlier, that this is 1 upon n factorial m factorial 1 upon pi alpha belonging to C d square alpha trace of f lambda d alpha, then minus alpha to the power n e to the power mod alpha square by 2 minus alpha to the power n alpha star to the power m. So, this is the expression. And now, if you use whatever we have the expression for lambda, what you will see is that this is equal to delta n m divided by lambda into n factorial into 1 minus 1 by lambda whole to the power n. Okay. This is what you will see. Okay. Now, of course, again this you can write provided real part of lambda by 1 minus lambda is greater than 0. Why? Because if you do this integral, what you will see is you will have an exponential of this form, exponential of minus lambda by 1 minus lambda times mod alpha square. There will be other terms, but this is what you will see. And this with this exponential in the integral, I mean this will converge provided you take the real part of this is positive. Okay, this is something like Gaussian integral. I mean not just Gaussian, this is moment of Gaussian integral. Now, if you look at this, it has a pole at lambda is equal to 0, right? Isn't it? It has a pole at lambda is equal to 0, right? Yeah. Now, I don't know, maybe we can simplify it further and see what is the condition, but that is okay. So, yeah, basically it tells you that this is equivalent to real part of lambda is greater than mod lambda square. Okay. So, now if you look at lambda is equal to 0, what is your f lambda? F lambda is equal to 0. What is this? You remember f lambda I can also write as exponential of a dagger a times ln lambda, right, because it is lambda to the power a dagger a. So, if I take lambda is equal to 0, what will I have? Huh?
It's not identity.
Lambda is equal to 0, what should be the term?
The thing is lambda to power a dagger a, right? Lambda to power number operator.
Lambda to the power number operator.
So
Yes.
0 to power 1, 0 to power 2, 0 to power 3.
So it would be exponent of minus infinity times a dagger a. Like ln lambda would be like minus infinity in that way.
Mm-hmm.
In the
No, it's 0, right?
yeah, 0.
It's a 0 null operator.
Null operator?
Yeah. Because you have 0 to power number operator. So it's 0 to power 1, 0 to power 2 is everything is 0.
But then D has a pole over there, but F is a 0.
Hmm. So, you know what will, well, yeah, this is bit tricky because you know lambda 0 is infinity, minus infinity. Okay, I mean minus infinity, if you think of it, because this is a positive operator.
Yeah.
Okay, so it should be basically 0,
Yeah.
but I mean there is a catch. Catch is that the ground state, okay, the eigenvalue, ground state eigenvalue is 0. Okay, so you know,
Oh, 0 to power 0 is there.
yeah,
So
so
it's
I can write it as n is equal to 0 to infinity n, sorry, what is that, how to write that, the eigenvalue expression, what is that,
N times Nn.
exponential of n ln lambda then nn, right? These are the eigenvectors, right? So, when I take lambda is equal to 0, of course, this is infinity and this will go away, provided n is not equal to 0.
But when F is 0,
Okay. So, when n is 0, then of course, you will have these terms, right.
yeah.
So, as a result, this is your f lambda is equal to 0.
So another way of seeing this is in that original expression lambda to power a dagger a.
Yes,
So a dagger is number operator.
yes.
So we go in the basis of, it's like lambda to power 0,
Hmm.
lambda to power 1, lambda to power 2. These are
Yes,
the
yes,
eigenvectors.
yes, yes, yes.
So 0 to power 1, 0 to power 2 are all 0
What about 0 to power 0?
is 1. We can just look at the function x to power x, limit of
Yeah, that
x
is
to
true.
power x as x approaches
But
0.
I think this is much easier, you know, you write it and then this is much easier.
But I mean, if you have exponential 0 times logarithm of 0.
Okay, so yeah,
Again,
so
you
that
have
is
to
also, yeah, you will have to take a limit, yes, yes. Anyway, so this is fine, eh? So, okay, so I have given this thing. So, therefore, so for lambda, so this thing I think what I have written here, pole at lambda is equal to 0. So, you cannot use this, but when lambda is equal to 0, f lambda is equal to 0 0, and then what about its anti-normal ordering expression? Can we have anti-normal ordering expression for this thing? Okay. Because this tells you it has a pole, right, lambda is equal to 0. So, either it will not have any anti-normal ordering expression or maybe it will have. Okay. Okay. So, and I will give you the hint, basically P distribution, as I told you, P distribution is connected with normal ordering, okay, but here we need anti-normal ordering. So, there is a connection of normal ordering, anti-normal ordering when I take the average value. So, basically if I look at the P distribution of the 0 0, I will talk about it more details. P distribution of this is a delta function. Okay. So, maybe there is a pi factor or something, I will have to look at it whether there is any factor. So, this is a delta function, and yeah, so this will have reflection in this anti-normal ordering. So, I will come back to this question of anti-normal ordering of this state later and see what happens there. Okay. So, I will have to treat it separately for the anti-normal ordering. From this formula I cannot do that.
Is there an easy way to see its normal ordering representation?
Normal ordering is easy, that you can figure out.
I mean, okay. I mean, is it a simple thing?
Well, not very simple. Problem is that how will you write it? So, the question you are asking is how will you write it as CNM a dagger to the power n a to the power m, right?
Okay, so we have that formula.
We have that formula, and this will be basically diagonal. Okay. So, that formula itself works. Okay, good. So, in fact, what you can see is that in fact, okay. So, this is, I said that this has a pole at lambda is equal to 0. Other than that, this is finite, right? When lambda is not equal to 0, this is finite, but that does not mean that this series will converge. What you can show is that this will converge for real part of lambda greater than half. Okay. So, which is much more restricted than this. Okay, good. So, so this is about this example, and now what I will do is so basically this example tells you that I mean for bounded operators you will have normal ordering expression, anti-normal ordering expression and symmetric ordering, but anti-normal ordering expression may not exist for certain range of values of lambda. And even for bounded operators also there are restrictions for the convergence of the normal ordering series, symmetric ordering series and so on and so forth. Okay. So, now it is time for connecting this operator ordering with distribution functions, which we have done little bit in some of the earlier classes, but let us do it systematically. Okay. So, we have this expression for any bounded operator 1 upon pi alpha belonging to C b square alpha trace of f b alpha b of minus alpha. This is in terms of displacement operators, and we know that displacement operator forms a basis, orthogonal basis. Okay. This we have seen, but this is not very useful in terms of all the phase space distribution functions. Okay. This expression is not that one cannot get directly from this expression. So, for that reason what we need is something more, but before that I introduce this S ordered displacement operator, which is d of alpha and s. S is a complex number. D of alpha and s is equal to d of alpha times e to the power s mod alpha square by 2. Why this factor? This is important, in order to restrict your some sort of singularity into finiteness, okay, by choosing this f properly, right. Now, what you can write is f is equal to 1 upon pi alpha belonging to C d square alpha trace of f d of alpha and s. Okay, so, I had to introduce this one. Now, I will have to take minus of this. So, what does it mean? It means that I will have to take minus alpha and minus s. Is that the correct one? Okay. Yeah, I think this is correct, right? Okay. But still this expression, I mean you can again show that you know that this will form a basis and all that you can do. But the problem is that still this is not very, this expression is not very useful to get the these different s ordered phase space distribution functions. So, for that what we need to introduce is a Fourier transform of this yeah. So, let me first introduce this Fourier transform and then okay. So, just before that if I take trace of f and g, f is this. So, trace of f and g for let us say two bounded operators, this will be 1 upon pi alpha belonging to C d square alpha trace of f d alpha, then trace of g d of minus alpha, right. Okay. So, this is what you will get, and you know by using this definition what you can show is that this is 1 upon pi alpha belonging to C d square alpha trace of f d of alpha comma minus s times trace of g then d of minus alpha comma s. Do you agree? It should be correct, right? Because from here you will get this e to the power minus s times mod alpha square by 2, and from here you will get e to the power plus s mod alpha square by 2. So, they will get cancelled. Okay. So far we know that if f is bounded then this is square integrable, if g is bounded this is also square integrable, right. This we discussed some time back. But what about this? If f is bounded we do not know whether this is square integrable, if g is bounded we also do not know whether this is square integrable because this s factor is there. Okay. So, now let us assume that trace of f d of alpha minus s and trace of g d of minus alpha s, these are square integrable. So, this is we assume that. Okay. Okay. So, then I can use complex Fourier transform, and you can see inverse Fourier transform of this relation, right. So, which will tell me that, so basically what you will take, so let me call this as f of alpha minus s. So, this is my definition, this is the Fourier transform 1 upon pi. So, this is complex Fourier transform, beta belonging to C d square beta e to the exponential of alpha beta star minus alpha star beta. So, this is the term which we will get to see, trace of f of d of alpha minus s times trace of g of d of minus alpha s, right. So, this is what you will see if I do the complex Fourier transform. Okay. Is that clear? Sorry, okay. So, this is not G, this is your f, just f. Okay. So, this is the Fourier complex Fourier transform of this function, and this exists. Why this exists? Because you assume that this is square integrable, okay, right. And similarly, you assume that g of alpha and s, which is 1 upon pi beta belonging to C d square beta exponential of alpha beta star minus alpha star beta. This is trace of g d of alpha s. So, this is your, sorry, not, oh, this should not be alpha, this is beta, otherwise it is not a Fourier transform. Okay. Yeah. So, this is your again complex Fourier transform of this weight function, and this exists because you have assumed that these are square integrable. If this is square integrable, this plus alpha is also square integrable. Okay. Now, because these two are square integrable, their Fourier transforms are also square integrable. Right. And you know that using the formula for Fourier transform, we have expressed trace of f g in this form. You can also express it in terms of the Fourier transform. F of beta minus s times g of beta s. Okay. Is that okay? I mean, this just you use the properties of Fourier transform. So, this one is same as this one. Okay. Right. Now, you know that, so now you look at the following properties. So, when I take s is equal to 0, then this is square integrable, this is also square integrable. Do you agree with me? When s is equal to 0, right? These are both square integrable. Okay. In fact, I can go a bit further. I can say that when real part of s is 0, then both of these are square integrable. Is that a correct statement?
You have already assumed them to be.
Sorry?
You have already assumed that they are square integrable.
That is assumption, but I know that f, both f and g are bounded operators. Now, let us not look at that assumption. So, now let us assume, so we know that when real part of s is 0, then I already know f and g are bounded operators. Then these two are square integrable or not when real part of s is 0.
So, that will just lead to oscillation.
Yes. So, therefore, it will be square integrable, right. What you will have is some phase factor. So, this will be always square integrable. Okay. So, these two, trace of f d of alpha minus s and trace of g d of minus alpha s, these are square integrable for real part of s is equal to 0. But now you will have to consider both of them. I mean not just real part of S 0. I mean what if real part of S is not 0? If real part of S is not 0, then real part of S will be either positive or negative. If it is positive, then you see that this is square integrable.
Yes.
If real part of S is negative, then this is square integrable, but not both of them are square integrable when real part of S is not 0. Okay. So, one of them will be square integrable. Okay. But throughout the discussion we assume that both f and g are bounded operators. Okay. Right. So, question is that you have for generic case, not necessarily whose real part is 0, you have a square integrable function and you have a function which is not square integrable. But still can you use both of them to get this thing?
Because in that formula,
Hmm.
effect of S cancels out.
Which formula?
This trace Fg is equal to 1 by pi f
Yes.
beta minus S
Hmm.
G beta
Hmm.
plus S. So
Yeah, so this is square integrable, but this is not, or vice versa.
but the exponential factor
Hmm.
which is causing the problem will cancel out.
Yes.
So there is no problem.
Yes, and we know from physically that if these two are bounded operators, their trace is bounded, trace is finite. Okay, good. So, keeping this thing in mind, what we will introduce is some new operator. In fact, this new operator may take care of this non-square integrability of these functions. So, let us consider that. What is the time now? So, what we look at is the Fourier transform of this operator. Now, you might say that at the level of operator, what is the Fourier transform? I mean this is not a bounded operator. Okay. So, but well, this may not be a bounded operator. Okay. It depends. So, for example, what will be this? This is magnitude of e to the power s mod alpha square by 2 times norm of d of alpha. Now, norm of d of alpha, this is unbounded, right? But if I take the trace norm, that means this 2, what will be this? This is okay, but what about this? This is also unbounded, but this one will be of course finite, right? Okay, fine. So, anyway, symbolically I can define. So, what I will define is this thing. This is complex Fourier transform of this, which I will call alpha s, whose definition is 1 upon pi beta belonging to C, d square beta exponential of alpha beta star minus alpha star beta. So, this is the factor which you will get for complex Fourier transform beta s. It is like complex Fourier transform of this modified or s ordered displacement operator. okay, right. And through this so through this Fourier transform, complex Fourier transform, so what you can do, this we have seen alpha minus s, this is where, what did I get, okay. So this is the, you can say, a complex Fourier transform of these weight function, right, complex Fourier transform of this weight function. And now if you replace this weight, this d of beta minus s, so you do not have to replace, you take it inside this integral, that I can do. So this will be basically the complex Fourier transform of d of beta minus s, right. And so this will be your trace of f t of alpha minus s. Do you agree with me? This is your definition, complex Fourier transform, just you put that here, and this is what you will get, okay. So simple. Recall that we had some such expression for this normal ordering, anti-normal ordering also, like in terms of density matrices, which was like p rho alpha star. What was that? That was trace over rho, and then this delta of this corresponds to normal ordering. So I think this is a minus alpha delta of a dagger minus alpha star, right. This is the kind of thing that we defined, okay. So if you take f to be a density matrix, which you can take because that is bounded and rest class, so you may think that this is, so this is for normal ordering. So normal ordering means s is equal to plus 1, okay. So you see that this operator, it looks like this. So when we first discussed this, we took as an ad hoc basis while defining the q function, p function, etc. But now it will come in a systematic manner, okay. Okay, good. And also you can show that g of alpha and s is equal to trace of g, then t of alpha and s. I mean, look at the definition and this is what you will get, okay. So simple expression, okay.
But it will still be bounded and unbounded.
G and f we have assumed to be bounded operators.
No, so small g and small f
Mm.
will still be bounded and unbounded like before.
Yes, it still it can
So
be.
what did we gain here?
Yes. So basically, what we will gain is a systematic expression for this thing. So I will show you that this is a, for real s, this is a Hermitian operator. So you can think of, if f is in rho, so you can think of like average value of this Hermitian operator with respect to your rho. So you measure this Hermitian operator with respect to rho and get this average value. So that is what we are looking for, which was not possible with the displacement operator, okay. Okay, good. This board is small, okay. Time. And now it is simple that if I take trace of f and g, which is 1 upon pi alpha belonging to c d square alpha, f of alpha and minus s, then g of alpha and s, and then you put this expression. Basically what you will have is 1 upon pi alpha belonging to C d square alpha. This is trace of f t of alpha minus s, then trace of g t of alpha s. So, which is what you will see. Okay. Now, what is big deal about this? So, now you choose any two state which need not be coherent state, any two state psi and phi, okay, and choose your G to be this one, outer product of psi and phi. This I can choose, this is bounded operators, right. So, if you do that, then you will see that this trace of f and g for this G, this is just put here G as this. So, what you will get to see is this is 1 upon pi, okay, alpha belonging to C d square alpha, f of alpha minus s, and now what about this? This is your phi t of alpha s psi, okay. This is what you will get, okay. So, and this is what? This is your phi f psi, right. Yeah. So, phi and psi arbitrary. So, this tells you that your f has to be 1 upon pi alpha belonging to C d square alpha f of alpha minus s, then t of alpha s. Okay, right. Such an expression of course we have obtained in terms of displacement operator. Okay. So, this is your weight function and this is your, that was your displacement operator, that is fine, but this is also you get, okay, or any bounded operator, this is what you will get. Okay, good. And this is true for all S, there is no restriction on S, okay, because I have used no specific value of S so far, okay, right. So, now let us look for certain properties of this T and then things will be clear. So, let me erase this part. So, number 1, T of alpha S dagger I do not think I should prove it, you have this definition, you take this dagger, what you will get is this is T of alpha A star, okay. So, just take the dagger, then this will be complex conjugated and dagger of these, and accordingly you can figure out. So, this means that T of alpha S is Hermitian for imaginary part of S is equal to 0, right, that means for real S, okay. So far so good. Number 2, if I displace this displacement operator beta S d alpha inverse or dagger, whatever you want to call. Let me first do it and then I will come back to T of alpha S, okay. So, what you will see is that this is equal to, with this phase factor, alpha beta star minus alpha star beta times d of beta s. Okay. So, this is what I mean, just you use the definition of d of beta s and then product rule of d alpha d beta, that will give you this thing. Okay. Right. So, now if you look at, so this is your property, and then using this you can show that d of alpha yes. So, using this what you can show is that T of alpha s, and this is very important, T of alpha s is equal to d of alpha T of alpha 0, not alpha 0, sorry, 0 s d of alpha inverse. Okay. How will you prove this thing? Basically, you take this expression for 0 T of 0 s from here and then apply this. So, basically you will have to use this rule. Okay. So, this means what? This means that the alpha dependence of T of alpha s, it comes from this displacement operator, right. So, if you displace, then the amount of displacement will be reflected in this T of alpha s through d of alpha, right. So simple. Okay. Now, we know that for real s this is Hermitian, right. This is what we discussed here. For real s this is Hermitian, okay, whatever be your value of alpha, because this T of 0 s for real s is Hermitian, therefore, for real s this is also Hermitian, because this is unitary operator. Moreover, the eigenvalues of this Hermitian operator for real s will be same as the eigenvalues of T of alpha s. Only difference will be in the eigenvectors, right. Okay. Okay, good. Number 3. Now, it is a little bit more, that d of alpha minus beta T of beta s d of alpha minus beta inverse, inverse means dagger, this is equal to T of alpha s. Okay. How will you do that? Just apply this on the left hand side and this on the right hand side of this. Okay. Huh? Yeah, this is what you will see. Okay. So, this is fine. This is how this T of alpha s works. And now, if you look at the, so what we need is structure of T of 0 s. How does it look like? Okay. So, T of 0 and s. So, this is the Fourier transform of d of beta s, right, because in the Fourier you remember this is your expression. So, if you take alpha is equal to 0, this is what you will have. Okay. So, this is what you will have, T of 0 s, and this you can write as 1 upon pi let us see, it is beta belonging to C d square beta e to the power s beta square by 2 into d of beta minus 1. Yeah. Okay, so this will be basically minus beta, but on integration minus beta plus beta does not make sense. This is what you will have. Okay. So, anyway, so I do not want to go all through all these details. So, basically what you will see is that okay, this I do not know why should you write this thing. This is I mean, this is we have already seen that this is 1 upon pi beta belonging to C d square beta. Of course, one should be careful when I write 0 s and then d of beta, then d of beta inverse. This is true if t of 0 s is a bounded operator. So far we do not know whether this is bounded operator or not, okay. But using this formula you can show that t of 0 s basically it will be of this form, okay, right. So, this is fine, this is okay. I mean, yeah,
I have a question.
yes,
So this T,
Yes.
we can use this T to get to phase space,
yes,
which I presume will use to go to P distribution in X.
everything, not just P distribution, every other distribution.
Earlier we were using this
Displacement
just
of-
the displacement operator.
Hmm.
We were also going to some space with that.
Yeah, but those are not very very useful to have a generic structure, okay.
And then we also had this bra alpha ket beta operators to go to space.
Yeah,
They also-
that is also true, that is also you can take, but the point is that why I introduce this, basically this will tell you, this will provide you a unified platform to deal with all the distribution functions.
But in the case of bra alpha
Hmm.
ket beta, that also takes us to a phase space.
In principle, yes.
So I mean, how does is that is a different kind of space than
No, phase space is same, phase space is same,
I mean, mapping is different. The
Yes.
same state will map to different function.
yes, exactly.
I mean, for example, in this case,
Hmm.
it has the existent S for which we'll get the displacement operator space, something like that. Not really.
No, for s is equal to 0, you will get the original displacement operator, right.
Oh, okay. Original
For d alpha s is equal to 0 is d alpha.
And then for what about bra alpha ket beta? Can we recover that also from here?
Yes, yes, of course.
How?
You can write the bra alpha ket beta, no, ket alpha bra, yeah, this one, right.
Ket.
Yeah, this you can write of course in terms of displacement operators.
No, but the phase space in which this one takes us.
Nothing like this one takes us. So, as I said, every phase space distribution function is related to a specific ordering of your operators. Operators means in this case density operator. Okay. So, whatever ordering you take, based upon that you will have to get the corresponding phase space distribution function. So, this will not be, this is of course not density operator. So, when I talk about the phase space distribution function, this is for density operators. So, depending upon the phase space, I mean the operator ordering of the density operator, you will get a corresponding phase space
So
distribution.
for S is equal to 0,
Hmm.
we go to symmetric order.
It goes to symmetric order.
So basically, displacement operator takes us to
Exactly, exactly, yes. Okay, now why I introduce this thing? So, this is a bit, so you will see a similarity with the example we considered earlier. So, remember we have this operator which this is what we have considered, and if we look at trace of f lambda d of gamma for any complex number. This is, I do not know, did I consider this, and if even if I not, you can calculate this. This is not difficult. Minus 1 plus lambda by 2 into 1 minus lambda mod gamma square. Okay, I mean just it's not difficult, you can figure out. Okay, right. Now, if you look at this trace of T of 0 s and D of gamma, where is that? Oh, I somehow missed that. Anyway, so you use the definition of T of 0 s, which is, so T of 0 s is this one, and then you multiply by D gamma and then take trace. Okay. So, this is also like exponential of s gamma square by 2. I mean, if you calculate things, this is what you will have. Okay. So, now you see a similarity, right. What is the similarity? If you choose s is equal to minus 1 plus lambda by 1 minus lambda, okay, and 1 minus lambda times f lambda is equal to T of 0 s, then you see these two, I mean you will have to, because this is a factor, I can take it out, take this side. So, you see a similarity of these two, right, because these two values are same.
So, they are the same operator.
These are the same operators, yes. Okay.
And if we do displacement, we will get the other unitary transformation using that equation. So you get
Yes,
the other-
yes, right. So, this is your S, and you can also this is equivalent to lambda is equal to S plus 1 by S minus 1. Yeah. Okay. Right. So, as a result, you can say that T of 0 s, this why I did this thing, because I wanted to have an expression for T of 0 s in terms of A and A dagger. So, what will be this? This is 1 minus lambda, and f lambda is lambda to the power A dagger A, and which is S plus 1. Oh, I will have to change this lambda also. So, basically this will be 2 by 1 minus S. So, S plus 1 by S minus 1 A dagger A. Okay. So, this is what you will have. Okay. Right. So, once you have this expression, now you take this T of alpha s, which is D of alpha T of 0 s D of alpha inverse. Okay. And this is again same as 2 by 1 minus s D of alpha S plus 1 by S minus 1 A dagger A D of alpha inverse. Okay. Right. Okay, good. And you will have to use this formula. So, let me erase this part. So, you need to use this formula, D of alpha f of A dagger A D of alpha inverse. This is equal to f of A dagger minus alpha star A minus alpha. I will not prove it, you can prove it, okay, for any well behaved function of A dagger A. Okay. So, if you use this, then what you will see is that T of alpha s is equal to 2 by 1 minus s exponential of A dagger minus alpha star A minus alpha ln s plus 1 by s minus 1. I mean this means you will have to take, you know, this is nothing but 1 minus s plus 1 by s minus 1 a dagger minus alpha star times a minus alpha. Okay. So, this is the operator T of alpha s that you get. So, this kind of trick we need to use occasionally. Okay. So, that is why this example was very useful. Okay. Right. So, now you see that therefore, what should be the s dependence of T of alpha s is bit complicated. Here is a prefactor and also s is here. Okay. Okay, good. So, now you can actually, you know, I told you that T of alpha s is Hermitian for real s, okay, but you can have again a decomposition of this operator. So, 1 minus s. So, you take the number operators basis number basis 0 to infinity s plus 1 by s minus 1 whole to the power n. Okay. You know, this comes from here like this one. Okay. So, this you have the spectral decomposition kind of thing. So, this is d of alpha acting on n, d of alpha acting on n dagger. Okay. Is that clear? This is in the number operator basis. So, you see that this is an operator whose, this is a spectral decomposition kind of thing. Of course, these values can be complex, but these are, you know, orthonormal states, okay, because d alpha is a unitary operator, and this is the spectral decomposition of T of alpha s. When s is real, of course, this is real. Okay. And what are the eigenvalues? So, the eigenvalue, so if you call it as E n of s, this is 2 by 1 minus s plus 1 by s minus 1 to the power n. So, this is the, so this is alpha independent eigenvalue. So, alpha dependence comes in the eigenbasis.
X is equal to 1 and divergence.
Yes. S is equal to 1 has divergence. Yes, that is true. And S is equal to 1 means, as I said, this is anti-normal ordering. I mean, S is equal to plus 1. And therefore, there is no wonder that you have this singular phase space distribution function for that.
Except for n is equal to 1.
No, no, any n, this is true.
Infinite to power 0 is.
What about E n s is equal to minus 1?
To power, and so yeah, so it's the only ground state will be there.
Yes.
N is equal to 0.
Yes. So, this is 1 for n is equal to 0, 0 otherwise, right. Okay. And so, you see that T of alpha minus 1, what will be that for, this is 1. So, T of alpha minus 1 is equal to
D alpha at n.
d alpha 0 0 d alpha in, right.
Replaced grounds.
This is the, and this is nothing but coherent state. Okay. Yes, I am done. Yes. Yeah. Okay. Good. So, we will stop here and then next time I will start from here and then I will go to the phase space distribution functions. Okay. So, this operator we will see is very useful.